So we've been talking about the neuron that is sending a signal, how it uses neurotransmitters to bridge that gap across the synapse. The sending neuron is usually referred to as the presynaptic neuron because it is before the synapse. However, the postsynaptic neuron that is receiving the neurotransmitters, we haven't talked too much about what happens when those neurotransmitters arrive at the postsynaptic neuron. What's happening is that these neurotransmitters are arriving to the edge of the dendrites of the postsynaptic neuron, and on the edge of those dendrites are proteins that span the membrane and actually act as receptors for those neurotransmitters. Specific neurotransmitters combine to specific receptors, changing the properties of the neuron. Let's take a look at the two most common type of receptors. Probably the most basic receptor, and probably one of the easiest to understand, is what is called an ionotropic receptor. An ionotropic receptor is a protein that spans the membrane of the dendrite of the postsynaptic cell and is a channel that allows the movement of ions through it, hence ionotropic. When a neurotransmitter binds to the ionotropic receptor, the channel opens. Usually it's closed, and this allows a flow of ions across it. For example, one ionotropic receptor allows the movement of sodium ions into the dendrite. We've already talked about how sodium ions are going to move inside the cell because of the electrochemical and chemical gradient differences. This is actually how a signal coming into the dendrite moves the charge of the neuron towards the positive as it moves towards the threshold back in the previous module when we were talking about the action potential. Let's take a look at the action potential chart and see what I mean by that, right? Remember, the neuron starts in sort of that negative charge range because there are more charged particles outside of the cell than inside of the cell. So what happens is if a dendrite receives some information, that ionotropic receptor might open up. And in this case, if the ionotropic receptor is a sodium ionotropic receptor, it's going to allow sodium to begin to leak into the cell. This is a positively charged ion that is going to slowly move our charge inside the cell positive. Okay? And if it reaches that threshold, then the sodium gates are going to open, causing an action potential. Right? So this whole part here where we see the movement from the resting potential towards the threshold can be caused by an ionotropic receptor being opened up, allowing the sodium in. But ionotropic receptors may be many different types of ions, not just sodium and not just positively charged ions. For example, one type of ionotropic receptor actually allows chlorine to leak into the neuron, and chlorine is negatively charged. So what's going to happen if chlorine leaks into the neuron? Well, it's going to move us into the negative direction. So what's going to happen to the ability of this neuron to fire an action potential? If you stop and think about it, I think you'll see that basically what happens is this neuron becomes less sensitive. In other words, it's going to take even more change in charge for it to fire. So rather than simply needing to cover that distance, it now needs to cover almost twice as much. So an ionotropic receptor that allows a negatively charged ion actually makes it more difficult for that neuron to fire. Whereas an ionotropic receptor that allows a positive ion in makes it more likely to fire, and if enough comes in, it actually causes the neuron to fire. So this reveals to us that there are at least two major functions that neurotransmitters can do. They can either be excitatory, which is moving the neuron in the direction of firing, right, making the neuron more likely to fire, or they can be inhibitory, making the neuron less likely to fire. So there are two main types of actions: excitatory, more likely to fire; inhibitory, less likely to fire. Oftentimes, a single presynaptic neuron firing isn't going to be enough to cause a postsynaptic neuron to fire. A little bit of that sodium will leak in, but it won't quite reach the threshold, and then with time, the sodium-potassium pump returns us back down to baseline. In order to cross that threshold, a couple things need to happen. We either need to have multiple neurons firing at once, or one neuron firing very, very quickly in time. So, for example, if it's one neuron firing quickly in time, you'll get the initial bump of sodium, and then a couple of milliseconds later, you'll get that second bump leading to the threshold. Or you can wind up with a situation where two neurons fire at the same time, causing the threshold to be exceeded right away. But also keep in mind that we can have neurons that are both inhibitory and excitatory. So on the one hand, you can have a neuron that would normally cause it to be excitatory, or another might cause it to be inhibitory, and if they both fire at the same time, we actually see no net charge in the cell at all. Right? So we can have excitatory and inhibitory, and then we can also have either two neurons firing at the same time, that's called spatial summation, or a single neuron firing very quickly in time, that's called temporal summation. Here's a figure that should also be in your textbook that demonstrates the temporal and spatial summation and the interaction of excitatory and inhibitory. If two neurons fire very quickly in space, we call that spatial summation. If a single neuron fires very quickly in time, it's temporal. Now remember, neurotransmitters can have either excitatory or inhibitory effects, and these interact with both spatial and temporal summation. There's another very different receptor that can be on the dendrite of the postsynaptic neuron that we should know about. These are called metabotropic. Ionotropic move ions across the membrane, hence ionotropic. Metabotropic can have much more complicated effects, altering DNA expression, activating a variety of ionotropic receptors, or even changing the metabolic processes of the neurotransmitter. Metabotropic receptors involve a protein that spans across the membrane, and when a neurotransmitter binds to it, something called a G protein is released. That G protein then moves into the postsynaptic neuron and can activate a variety of effects. Said these can be a wide range of effects. It's much slower, though, than the ionotropic. Generally speaking, we think of ionotropic effectors as being very, very quick, but also very, very temporary, whereas metabotropic receptors can often be much slower for their effect to be seen, but can have much, much longer or even permanent effects on not just the neuron, but the nervous system as a whole.